Hi, my name is Jim, and the topic for discussion today is series parallel circuits. Now, in themselves, it's not a difficult concept if and only if you're familiar with the analysis of series circuits and with the analysis of parallel circuits. It's just a matter of combining them, and we can solve some fairly complicated circuit diagrams using those techniques. So we have two examples today, and we're going to begin with this one. We have a 12-volt source. It's in series with R1, and R1 is in series with this network of resistors here, comprised of 3 parallel resistors, and this is in series with another network of resistors that is comprised of 2 resistors in parallel. So our first order of business here is to simplify this and find the voltages at point A, node A, which is very easy, that's 12 volts, node B and node C, and once we have those voltages, we can decompose this circuit and find every single circuit parameter that we desire. So to do that, we're going to convert this into a series circuit, and just a little foresight of where we're going here, it'll look like this: 12 volts, and this will be the A20. This here resistor will be the parallel combination of these guys, which I call R equivalent A. And this resistor here will be the parallel combination of these, which I call R equivalent B. So the first step here is to figure out what the total resistance of this will be. And when you do this in parallel circuits, always be aware that the total resistance is less than the lowest resistance in a network. Contrarily, in a series circuit, RT is going to be higher than the highest resistance in the network. So with this, I'm saying R equivalent A is equal to 2.2K, and this is an in parallel symbol, with 2.7K in parallel with 3.3K, and then I exhaustively work through this using the equation for parallel circuits that we discussed last time. So that involves the conductance, which is 1 over 2.2K and 1 over 2.7K and so forth. And I was careful to write down every step here, so there's no questions here. And that would be equal to 1 divided by 454.5 microsiemens plus, and then the same with the rest of these. Adding up the denominator gives us 1 divided by 1.28 millisiemens, and then finally doing the reciprocation gives us 887 ohms, and looking at this network, that appears to me to be a reasonable value. So that would be R equivalent A. So next step is to find R equivalent B. I can use the simpler technique to find the equivalent resistance of these by using product over sum, and if we do that, we end up with RB equals 600 ohms. And remember, when we do this is a resistance times resistance, so the unit here is going to be R squared, and this is a resistance which is going to be R. So from the standpoint of units, when we divide R squared by R, we get R, which is the resistance. Actually, what I should say here is not R squared, but omega squared. Yeah, let's do that. That's a little bit better. So we end up with 1 omega, which is the correct unit. And having the correct unit is a very effective technique in troubleshooting. If you end up with the wrong units, chances are that your solution is incorrect. So once we know that, and we now have this circuit with VB and VC of interest, it's just a matter of using voltage divider to find what VB is. And note in the numerator here I have the 887 ohms. That would be this in series with the 600 ohms, which would be this. So the numerator consists of those two terms relative to ground divided by R total, which I've explicitly written down as the 3 terms here. So working that out, what I find is that the voltage at VB is 7.735 volts. Now what you have to be careful of when you do this on a calculator is that before you do the actual division is you put the denominator in parentheses. Otherwise what will happen is the numerator will be divided by 820 ohms, and then this will be added to the total. So the precedence operation here is very important, and you need to use parentheses correctly. Likewise, looking at VC, it's the same thing. The numerator now contains only the 600 ohm equivalent from VC to ground, and that gives us a voltage of 3.12 volts. Next, what we want to do is find VBC, and that's a doubly subscripted variable that's explicit. Now, VB is also a doubly subscripted variable that's non-explicit, and the second variable in here would be ground. So every single variable you have, voltage, was always a doubly subscripted variable. And just think about taking a DMM. What are you going to put it across? From what to what? So ground would be the default if you don't have a second variable listed here. On the other hand, VBC is very different. It's saying the voltage with between node B and node C, and the way that decomposes in VB minus VC. So what I would have would be the 7.735 minus 3.12 volts, and that leaves us with a voltage drop, DROP, that may or may not reference ground, very important, of 4.615 volts. So if I put the negative lead of a meter here and the positive lead of a meter here, I would expect to see something in the vicinity of 4.62 volts. Okay, so once we got that, and I've just redrawn this diagram, let's find some circuit parameters, and the first is going to be the total current flow, which would be this current right here flowing out of the source into our resistive network. So this is just a matter of Ohm's law. I total would equal V divided by R total. That would be everything to the right of my hand. And 12 volts divided by R2, 3.07 k ohms. And let me see, I didn't mention that number before, so I'll go back, find out where that is. Here we go. R total is 2.307 k ohms. Now, that's just a sum of these three resistors, and note this, I made a mistake when I wrote this down, and what I did is transpose two digits. That's a very common thing that I do, and that's why it's important to have all your steps laid out clearly, is when you go back and look at things, is that it's very easy to see this, or if you try to do this in one massive calculation on one line in a calculator, it could be troublesome to try to find mistakes like that. So dividing this through gives us a total current of 5.20 milliamperes. And you can also find R3, and that would be equal to VR3 divided by R3. And VR3, which would be the voltage across this resistor here, is going to be our VBC, which we calculated on the previous page, divided by R3. And that comes out to be 1.709 milliamperes. Likewise, IR2 would be our VBC divided by 2.2K, gives us 2.1 milliamperes, and I resistance 4 comes in at 1.398 milliamperes. So if we add these all together, and I'm doing that here, my expectation is we should end up with I total. And the reason is because of Kirchhoff's current divider law. So this is flowing into node B. We have a current flowing out here, current flowing here, and a current flowing here, and we can't leak current, we can't leak voltage, and we can't leak power. Everything has to be accounted for, and that gives us 5.205 milliamperes, which, with due respect to round off, is the correct answer. Next, we can find the current through IR6, and that's simply going to be VC here. That would be this guy. The VC would be at that top node of that guy, and that would be 3.12 volts divided by 1.5K, which gives us 2.08 milliamperes. And likewise, IR5 would be VC divided by 1K, gives us 3.12 milliamperes. And again, just as a sanity check, is the sum of this current and the sum of this current has to be equal to I total, and adding these up we get 5.2 milliamperes, so I'm quite pleased with that. Next, to find the power in resistor 2 would simply be equal to the voltage across the resistor, important, that would be VR2 squared divided by R2, and that would come out to be 9.681 milliwatts. Likewise, if I wanted to find the total power, the easiest formula would be V times I total, and that gives us 62.4 milliwatts. So what you can see here is we have three power equations: V times I, V squared over R, and I squared times R, and you want to use the simplest one. There's no sense in this case of, well, we already solved for I, but if I didn't, I could just avoid a step by using V squared over R directly. So I'm pretty happy with the results of this circuit. Now let's take another circuit here, and this is kind of drawn strangely, we'll say. Usually in circuits, the source is on the left, and in this case I've drawn it backward. I see the positive side of the battery is connected to ground. I see I have a diagonal resistor in here. It's kind of different. And the analysis of this is going to be exactly the same as any other thing, any other circuit that we analyze. And the important point to see here is that the current flow in this out of the source is going to be toward ground. Now, you can solve this as it's drawn if you're comfortable with the diagram. If not, convert it into a standard form. Move the source over to the left, combine R1 and R3 that are obviously in series, and put these two resistors in parallel with the 470K. So this would be the conventional way of drawing that circuit. You don't have to do this if you're comfortable with analyzing that. If this gives you insight in how to solve the problem, by all means redraw it. Redrawing is a tool to solve problems. So what I've done is combined our R1 and R3 together, and I call that, resistor equivalent 1. And that comes out to be 370 ohms. So these two resistors would be 370 ohms, and that's in parallel with our 470 ohm diagonal resistor. Next, I want to find our total, so that would be R2 in parallel with our equivalent, and I'm going to use product over sum, and that gives us a total of 207 ohms. I total here then would simply be equal to the voltage 8.5 volts divided by our total 270 ohms, which yields 41.06 milliamperes. Now, I don't have a negative current here, and the reason I don't is because I defined the current in this direction. If I defined it in the other direction, it would be negative. And in some circuits, you have to be very, very careful of that. The direction of the current flow physically is the same as the definition of the current flow, then it's a positive current. So next I want to find VR3, and this time I'm going to take negative 8.5 volts, and across this here is going to be the 150 ohms. I want the voltage across this here resistor, and that's going to be divided by our total, and that now equals negative 3.446. So you have to be careful that you don't drop the sign on this. It would be a negative voltage referencing ground. So VR3 expressed as a doubly subscripted variable would be VR3 to ground. Likewise, to find VR2, just a matter of doing the same thing, which yields negative 5.04 volts. And then finally, for a sanity check of adding these two together, this would be a negative voltage plus a negative voltage, ends up giving us a source voltage, or a total voltage drop, which is equal to the source voltage of negative 8.5 volts. So that checks out. Further, if I wanted to find VR2 without going through this step, there's nothing wrong with taking the total voltage in the circuit and subtracting from it VR3. So if we have a total and we subtract a known quantity, what we're left with is this guy. And this, again, works because of Kirchhoff's voltage laws. This may be a simpler calculation. So in doing that, here I set this up, and you have to be very careful of signs. VR2 equals negative 8.5 volts minus a negative 3.446. The rules for doing this is change the subtract to add and use the opposite of the subtrahend, and that ends up giving a VR2 of negative 5.05 volts, which corresponds well to our other answer, wherever it is here. Oh, here we go. Negative 5.04 volts. So that'll conclude in series parallel circuits, and why it's very important that you get this topic down comfortably is because in AC circuits you're going to be working with complex numbers, and the circuits will be similar, and the analysis technique is exactly the same except for the complex numbers. Now it's not hard, it's just more detail that you have to keep care of. So that'll conclude for series parallel topic, and thank you for watching.